Chapter 8, Simplifying Fractions and Rational Expressions. And so, like Chapter 7, we're still dealing with these rational expressions. And what we did in Chapter 7 was just talk about the domain of a rational expression or a function specifically. Well, now we're going to talk about how to simplify them. So we start this chapter with the definition, and that is the definition of relatively prime. Okay, so we've talked about prime, especially in intro algebra, and I think we've talked about prime along the way to chapter 8 and here as well, but now we're talking about a different term, relatively prime. Okay, and it's similar to prime, but not exactly prime. We're talking about two numbers in particular, and their greatest common factor is 1. Okay, so for instance, in example 1, we say that, and it's asking us the question, are they relatively prime? Well, another way to phrase that same question is the biggest number that divides 12 and 15 1? If that's the case, then yes, they are relatively prime, but 12 and 15 are not relatively prime. If we write out the divisors of 12, then we're going to get a list here. 1, 12, 2, 6, 3, and 4. And then likewise, if we write out 15, then we have 1, 15, and then 3 and 5. So if we compare the factors of two numbers, and they have a divisor that's bigger than 1, a common divisor, for instance 3 for 12 and 15, then they're not relatively prime. Okay, and why that's important is because if we were to have a fraction 12 over 15, then we could simplify that fraction, which is the whole point of chapter 8. So what we can do at this point with 12 over 15 is divide the 3 out of the top and the bottom, and we get 4 over 5. Okay, this is the way we usually simplify fractions, and with numbers that's completely legitimate. So I'm going to rewrite it a different way, but that's simply so that it looks or more closely resembles how we're going to end up simplifying rational expressions. So again, say if we had the 12 over 15, we could factor these. Okay, we could factor it in the numerator and the denominator. So in other words, I could take 12 and I could write it as a 3 times a 4. And then likewise 15, I could write it as a 3 times a 5. And so when we factor the numerator and denominator, we see that they have common factor on top and bottom, this fraction as a whole. And so we're simply going to strike out that 3. 3 divided by 3 is 1. And so we're left with 4 over 5. Okay, and so this is what it's really going to sort of look like in this chapter 8 when we simplify expressions. Now, the second example, we're comparing two polynomials. And if you'll remember, for instance, and this is not one of the polynomials, when we first started talking about factoring and we talked about squares, we said that the sum of squares is prime. That's because we cannot write this as the product of two separate factors. We can't break this up. So this was prime, but when we're talking about relatively prime, we're comparing two things, or maybe three things. Okay, in this case we're comparing two polynomials, and here we have x squared minus 4, which is not prime. We can factor this as a x minus 2 and an x plus 2. Likewise, x squared minus x minus 6 is not prime either by itself. So we write x minus 3x plus 2. And so we see that when we compare their factors, they share a common factor. Common factor. So when we say, when we compare these two polynomials, we say that they are not relatively prime. Okay, they share a common factor, x plus 2. Now, another definition, chapter 8. A fraction is said to be in simplest form if we cannot divide out an extra divisor from the numerator or denominator. Okay. Alright, so at this point, the workbook shows us or refreshes our memory on how to simplify some fractions that have variables in them. And here we're looking at the quotient rule, and we've sort of been using these along the way, especially when we're talking about the greatest common factor technique in chapter 3. Here we have an exponent raised to the power of 0, and that equals 1. Okay, so likewise we could have y raised to the 0 power. It would equal 1. We could have a number such as a 5 raised to the 0 power. That would equal 1. And we can also have several variables, for instance x, y squared, z to the 5th. And if this entire term was raised to the 0 power, then it would simply reduce to a 1. Okay, so this rule applies to a lot more situations than is obvious. Rule number 3, if you have a negative exponent, for instance, if we have a x to the negative 2nd power, then we could simply, to get rid of this negative exponent, we could take the x to the denominator and then write the exponent as a positive number. Likewise, if we had a fraction and there was a negative exponent on the bottom, say for instance we had maybe negative 3 and then a y to the negative 5th power, and we just wanted to get rid of the negative exponents, then we could simply take the x and the y into the numerator and then write their exponents as positive numbers. Okay, so this is how we deal with 0 exponents, and this is how we deal with negative exponents. We simply move it to the opposite side of the fraction. And now we see the product rule for exponents, and it just simply tells us that if we have two of the same variables multiplied together, they can have different exponents, and in that case we could reduce it to one x variable and simply add the exponents. So an example of that would be x squared times x to the 3rd power. We could simply just write this as a 2 plus the 3, an x to the 5th power. If we had a y squared times an x to the 3rd, we could not simplify this. The variables have to be the same in order to add the exponents. So this can't be reduced in any way. Let's see, if we had let's say we had an x squared, then a y, and then an x to the 5th power. then the only thing we could do is combine the x variables, add their exponents 2 and 5 and get a 7, and then just write the y off to the side. And finally, I guess I'll mention one more example. Say for instance we had an x to the 4th power times an x to the -3. Instead of moving this variable, since it has a negative exponent, we could move it to the bottom, but instead of doing that, we could just apply this product rule and say 4 plus a -3, and that would give us an x to the 1 power. So we're going to be using these properties of exponents while we're trying to simplify these rational expressions. So page 82, we have a couple examples, start examples here. And so what they mention here is that we could avoid negative exponents if we just simply subtract the smaller exponent from the larger one. Okay. So let's see, and they're showing us two different ways that we could work the same problem. You see that this rational expression has a 15x to the third, y to the -2. Likewise, this one has the same numerator, and then they both have 10x squared over y, so, or 10x squared y on the bottom. So they're working the same problem here. They're trying to simplify it, and they do it a couple different ways. The first thing we see here, which doesn't really change from one to the other, is that what they've written 15 is 3 times 5. They factored the numbers simply. And then over here we see 10 factored as 2 times 5. Alright. Then they show an x squared and an x to the third on the top and the bottom of the fraction. And so they combine those. They say x, they keep the 3 on the top, and then they subtract the 1 on the bottom, minus 2. Alright. Then they simplify the y's, and they keep the y on the top, which has an exponent of a -2, and then they subtract the 1 on the bottom, strictly following the quotient rule as it's shown in this workbook and most other textbooks. The rule is usually set up to where you move the bottom variable and you combine it with the top. Okay, so they subtract the 1 from the bottom. See, this for the y, this was a positive 1, and the quotient rule dictates that you subtract exponents. So minus 1 on the top. Now, when we do that, the 5's cancel, so we have 3 and 2. And then for the x variable, we have 3 minus 2, and we get a 1 here, which is understood. It didn't need to be written. But now we see that for the y, we have a -2 minus 1, and we end up with this negative exponent. Now, to fix that, it's real simple. We simply move the y to the denominator and put it beside the 2. And here we have the simplified version of our original rational expression. However, not following this little tip sort of adds in an extra step here at the end. So let's see what we do differently in this second worked example. Again, we have 3 times 5 and 2 times 5. We simply factored 15 and 10. And then once again we have x, and we kept the 3 on the top, and we subtracted the exponent from the bottom. But in the end, 3 minus 2 just simply gives us a positive exponent, x to the 1. So we're happy with that part. It's the y part where we want to make a change. Notice that in the first example, we moved the y to the top and subtracted it. But 1, the exponent of the y in the denominator, 1 is actually bigger than the negative 2 that's on top. So what we do instead is we keep the y to the first power on the bottom, we subtract this minus sign is because of the quotient rule, and then we move the negative 2 and combine it with the exponent on the bottom. So we move the smaller exponent. And what we end up with is a 1. Okay, if I go down here and I work out the signs, minus minus is a plus, so this ends up being a 1 plus a 2, and it now gives us a positive exponent. And so we don't have this extra step where we have to fix one of these negative exponents. They're both positive, and so this was our last step, and we get the same result that we did up here after having completed 1, 2, 3 steps. So moral of the story is move the exponent with move the variable with the smallest exponent. Okay, and I'm going to stick with that rule myself. Nobody wants to do a lot of steps that are unnecessary. So example 3, we factor the numbers. 3 is prime, so we can't factor that unless we write 1 times 3. 6, however, will factor as a 2 times a 3. So we see that we can knock out a 3 here, but I will go ahead and handle the variable parts. We have an x on the top and the bottom, and so what we do is we pick out the x with the largest exponent, and it's going to stay where it's at, and we're going to move the other exponent, the smaller one, and subtract it from the larger exponent. So we write an x on the bottom in the denominator one place, and we write 4 minus 2 as its exponent. Now for the y, the larger exponent is attached to the y in the numerator. So we keep the 3 and we subtract the 2. We subtract the smaller one from the larger one. And so now the way we have this set up, we shouldn't get any negative exponents that we have to deal with. So 3's cancel, and we have a 2 in the denominator, and then all that's left on the top is a y. 3 minus 2 for the exponent is a 1, and we don't actually have to write that 1 there. In the denominator we have x to the 4th minus 2, and that becomes an x squared. And this is our simplified expression. Example 4, we factor 40, and I'm going to factor it as a 4 and a 10 because 10 is the biggest number that divides 40 and 30. And then I'm going to write 30 as a negative 3. Picking up this negative here, we can't just drop it. But negative 3 times 10 would give us the negative 30. So from here we just simply see that the 10's cancel out. Now for the x, y, and the z. We pick the x that has the larger exponent, and then we take the exponent from the other one, and we subtract it from the larger one. So one subtraction symbol is going to come from applying the quotient rule. The other one comes from the negative exponent on the bottom. See negative 5 here. Okay, the y, its larger exponent, is also on the top, and we have the smaller one on the bottom, so we'll take the smaller one, the 2, and subtract it from the 7 on the top. And then for the z's, negative 1 is bigger than a negative 3, and so we'll keep the z on the bottom where the larger exponent is, and we'll subtract the smaller one from that exponent. So remember, when you're dealing with negative exponents, you're going to have a minus minus situation. So it's not enough to just simply put a minus 3 here. That would be incorrect. So we have the 10s cancel. We're left with a 4 and a negative 3. And in the numerator, we have a negative 2 minus minus is a plus. So this is a negative 2 plus a 5, which is a 3, and it's positive. For the y, we have 7 minus 2, which is a 5. And for z on the bottom, this is a negative 1 plus minus minus plus a 3. So that becomes a positive 2, and there's no need to move any variables around because of negative exponents. And that's always going to happen if you move the variable with the smaller exponent. We moved this x, we moved that y, and then we moved this z to the bottom. Okay, so our first type of rational expression that we're going to simplify is one that simply only has one term on the bottom in the denominator. When that happens, we separate it up into several fractions. So on the top we have 1, 2, and 3 terms in this polynomial in the numerator. And so we break it apart into 1, 2, 3 fractions. Now, the denominator simply just gets copied underneath each fraction. 4x squared y, 4x squared y, 4x squared y. And then the first two are subtracted because the sign of the second term in the numerator was a minus. It was subtracted, so we just keep the signs, and then we had a plus 4xy, so this is these two fractions here are added together. So we keep the signs when we break apart the fractions. We copy the denominator under each one, and then we just separate the terms on top of the fractions. And from there, it's almost as if one problem has broken up into 3 simpler ones. So we're going to simplify each of these 3 fractions separately. So a 12 can be written as a 3 times a 4, and here I guess they factored 4, 1 times 4. So what we see is the 4's cancel, and we're just simply left with a 3 and a 1. Then if you look at the x's, they kept the x on the top, x to the third, and they subtracted the smaller one from the bottom, so we see a minus 2 there. And then y squared, take out a y, we have y squared minus 1 on top. And so they go to each individual fraction and they simplify it. The first one, we're just left with a 3x and a y. And you see that everything on the bottom canceled out, so we don't really have to write this first one, this first term, as a fraction. We don't have to write the denominator along with it. It canceled out. And then we see the simplified version of the last 2 fractions. So the point of this example is to show that whenever we have a denominator that only has one term, we break it apart into separate fractions or rational expressions. So here we have one term on the bottom, and then there's 2 terms on the top. So this is going to break up into 2 fractions, and they're going to be added together because we have a plus sign between the 2 terms on the top. So this can be written as an 8x to the third y 4, and then we just put the 3xy on the bottom. The second fraction will be 6x squared y squared, and then a 3xy on the bottom. Okay, 8 and 3 do not share any common factors, so we're stuck with 8 and 3. Now, the top and the bottom both have an x and a y, but the exponents of the two variables on the top are bigger than the ones on the bottom, so we'll keep the 3 from the x, and on the bottom the x has an exponent of 1, so we subtract 1 from the 3 on the top. Likewise, the 4 is bigger than this 1 on the bottom in terms of the exponents of the y's, so the y stays on the top and we subtract a 1 from the 4. Okay, 6 divided by 3 is simply just a 2. So we simplify the numbers, and then we focus on the variables. Again, the numerator has an x and a y, denominator has an x and a y, but the exponents on the top are the bigger ones. So for x we have x on the top, and we have a 2 minus a 1 from the bottom. And then for the y's, same situation, 2 on the top, 1 on the bottom, so we keep the y on the top, and its exponent is 2 minus 1. So we'll go back and carry out the subtraction with the exponents. For this fraction, the only thing left on the bottom is a 3. The x has an exponent of 3 minus 1, which is 2. 4 minus 1 for the y is 3. And for the second fraction, the fraction bar really isn't necessary because nothing's left in the denominator. So I'll erase that. And a 2 minus 1 is an x to the 1. And once again for the y, 2 minus 1, we're just simply left with a y. So here is our simplified version of example 5. Example 6. Notice that there are two terms, 1 and then a t3 h to the negative 1. That's our second term, and in between them we have subtraction. So we're going to have one fraction subtract another fraction, and we're going to split it up this way because there's only one term in the bottom of the original rational expression. So we take the at squared and we just copy it in the denominator of our two fractions, and then we split up the numerator into write the m first, and there we have it. So now we just focus on simplifying these two fractions separately. Alright, the first one, the only thing common to top and the bottom is an a. So the m and the t are just going to go along for the ride. Okay, we don't have a problem with the m or the t because you see they're positive exponents. For the a, on the other hand, which one has the bigger exponent? The one on the top. So that's the variable that we're going to keep, and we're not going to write the a on the bottom now. The a on the top had an x, or a 2 as its power, so a squared on the top, and we still have to address the a on the bottom. Its exponent was a 1, and so we just simply take that exponent and subtract it from the 2. Now, our second fraction here, the only thing that's common to the top and the bottom is the t. And now we have another issue, that we only have one h, but this h has a negative exponent. So we're going to move this one to the bottom. And as far as the second fraction goes, the a is okay because there are no other a's on top, and this a on the bottom is understood to have a positive exponent. One's not written for it. Now, for the t, we keep the t3 on the top because the power of 3 is positive and it's bigger than a 2. And we subtract the 2 from the bottom from the exponent on the top. And we just simply don't write a t in the denominator anymore. Now, with this h have a negative exponent, we simply write it in the denominator, and that negative 1 becomes a positive 1. It's not a 7, that's a 1. Kind of looks like a 7. But here we have it. All we have to do now is carry out the math within the exponents. 2 minus 1 just gives me an a to the first power. Everything else within that fraction is okay. For the t, we have 3 minus 2, which is 1, and we really didn't have to write that 1, so I'll leave it off. A is okay, and then now our h has a positive 1 for an exponent, so we can just simply drop the plus 1 and write an h in the denominator. And here we have our simplified version of example 6. So 7, one more example of where we have a monomial in the denominator. One term in the denominator, we break apart the numerator into separate fractions. Okay, there's our first one. And we simply just copy our denominator in each one. We have a minus 10 here, so I really want to put a subtraction symbol there. So minus 10x squared y squared, and then we copy down our denominator. Alright, 4 and 6. What is the biggest number that divides both 4 and 6? That would be a 2. So 4 divided by 2 is 2, 6 divided by 2 is 3. So we reduce the fraction for 6. For the x's, they have the same exponents here. And so what we could do, well, something divided by itself just cancels out. But if you want to see what happens with the exponents, we could write negative 1 minus a minus 1. And then with the y's, same situation. We could write y2 minus 2. Alright, and we're going to get 0 exponents there. And I'll show you what happens with that in a minute. The second fraction, again, 8 and 6, their largest divisor is 2. So 8/6 reduces to a 4/3. Now our x's have different exponents. The 1 on the top is a positive 1, and so the negative 1 on the bottom is the smaller one, and so we get a minus 1. And now for the y's, the 2 is bigger than the negative 3 on the top, so we're going to keep the y on the bottom and subtract the minus 3 from the top, so we end up with minus. And now for the last one, again, 2 divides 10 and 6, and we get 5/3. And for the x's, the one on the top has the larger exponent 2, and so we write 2 minus minus 1. And then for the y's, we have y squared, y squared. Those match up. So usually when you're working this problem, what you're going to do in situations like this is just cancel them out, and you wouldn't even write a y over here. Okay, I did this first fraction a little differently. The x minus 1's would cancel and the y squareds would cancel. So normally you would just cross these out, but I just want to show you what happens in regards to the exponents in this first fraction. So we have a 2 over a 3, and then a negative 1 minus a minus is a plus 1. Negative 1 plus 1 turns out to be a 0. So this is x to the 0 power. On the bottom we have 2 minus 2, which is also 0. So this is y to the 0 power on the bottom. For the second fraction, we have 4 over 3, and then x to the 1 minus a minus is plus 1. So this becomes an x squared. For the y, we have 2, and minus a minus would be a y2 plus 3. Minus minus is plus. So in the end, this is going to end up being a y to the 5th power. And for our last fraction, this x2 minus minus 1 is simply just a 2 plus 1. So we write x to the 3rd power. And all of the other variables canceled out. So this last fraction is finished. But now the first two fractions, we have a little more to do. This first one just ends up being a 2/3, because an x to the first and an x to the 0 and a y to the 0 is simply just a 1. X to the 0 is a 1, y to the 0 is a 1, and so this fraction is really just a 2/3. We don't need these 1's here. So I'll go back and erase them. For the second fraction, we still have 4 over 3, an x squared on top, a y to the 5th on the bottom. And now we're just simply copying down the third fraction, 5x to the 3rd over 3. So here is our final version. It's totally simplified. This is the final version of example 7. Now we look at the situation where there are more than one term in the denominator. And what we do in that case is we factor both the numerator and denominator. Okay? Instead of just splitting it apart in different fractions, we now have to factor it. We can't do it the way that we did in the previous examples. So you see here that 8x plus 16 is factored as an 8 times an x plus 2. And all we've done here is take out our greatest common factor. 6x squared minus 24 becomes a 6 times an x squared minus 4. So in the next step, x squared minus 4 is broken up into two fractions, or factors. And we now have an x plus 2 and an x minus 2 on the top. And the x plus 2 on the top will now cancel with the x plus 2 on the bottom. Like that, just like numbers do. The 6 and the 8 factored into a 3, 2 and a 4, 2, and just like this x plus 2, the 2's cancel. So in this case, we're really just striking a lot of things out. I guess you could say the factoring is the hardest part. But now we just simply write what's left in the numerator a 3, x minus 2, and then in the denominator a 4. So we're factoring the numerator and denominator in order to simplify these. So we'll work one on our own. Example 8. X squared minus 9 is the difference of squares, and so this is going to factor as a x plus 3 times x minus 3. And now on the bottom, two numbers that add to give us 3, or I'm sorry, multiply to give us 3 and add to give us 4. So we write x plus 3 and x plus 1. And we see that in both the numerator and the denominator we have an x plus 3. So just like the numbers canceled in the fractions that we simplified above, the polynomials will cancel if we see that there's one that's common to both the top and the bottom. So we strike out the x plus 3 and we just simply write x minus 3 and x plus 1. And if you're good at factoring, you'll see that these go a little bit quicker than the ones where we have to break up the fraction into several fractions. So here we go again. Factor the denominator, x plus 2, x minus 2. Factor the numerator, x plus 5, x plus 2. Just to double check these, a 5 times a 2 gives us the 10, and then a 5 plus a 2 gives us the 7. This was the difference of squares, and so we write first square root, second square root, first square root, second square root, and then we just put a different signs between the two. Once we've done that, you see that there's a x plus 2 in both the numerator and denominator. So, and this is the numerator, this is the denominators, but they cancel out. So on the top we write x plus 5, and on the bottom we write what's left, x minus 2. And that finishes example 9. So these go pretty quick. This one we can use a greatest common factor and take out 21, and we're left with an x minus 2. On the top we can factor out a 14, and we get an x squared and a let's see, what do we get, a minus 4. Now x squared minus 4 will factor further, and we want to factor these as far as they'll go. Now the bottom will not factor any further, but the top is the difference. It has a 14, yeah, but this part is the difference of squares, so it factors as the first square root, second square root, first square root, second square root, and between the two we just put a plus and a minus. And so now that they're fully factored, denominator has an x minus 2 and the numerator has 1 as well, they cancel. But now for the numbers, a 14 and a 21 are both divisible by 7, so we write divide by 7, divide by 7. So we're going to factor out a 7 from the 14 and 21. This becomes a 2 and a 3, and on the top we're left with the x plus 2 off to the side. Example 11. Um, this numerator is the difference of cubes, and I'm going to write out first cube root minus the second cube root. That's how the difference of cubes factors. The second factor is a trinomial. We square the first cube root, we square the second one, and so 2 squared is a 4. And then we just multiply the two together. And the second sign is different than the first, and the third is always plus. Our denominator is going to become, let's see, two numbers that multiply to give me a negative 6 would be plus 3 and minus 2. And they also add 3 minus 2 to give us the b plus 1. So denominator factors as an x plus 3 and an x minus 2. And you can see that we have something common to both the top and the bottom. X minus 2 cancels out. And so in the end, all we have is an x squared, 2x plus 4 on the top, and an x plus 3 on the bottom. So it is very important that you are familiar with factoring to be successful with Chapter 8. So like I said, factoring is important. If you're not comfortable with it, then just simply keep going back to those previous chapters, refreshing your memory, and get more practice with factoring, because the better you are at it, the more it's going to pay off. Alright, this last part of the chapter is just pointing out a simple situation that can happen, and it might throw you off. You might not realize that the rational expression will reduce, and that's simply because there's an extra minus sign floating around. So here we have an example, 3 minus x, and on the bottom we have an x squared minus 9. Well, x squared minus 9 breaks up into an x minus 3 and an x plus 3. And if you keep the top the same, you'll notice that, yeah, x minus 3 and minus x plus 3 are sort of similar, but they're not exactly the same. So you can't just cancel this and this. These are not exactly the same. They have sort of the same signs and the numbers, but they're not the same factor. The difference being, the 3 is plus, this 3 is negative, this x is plus, and that one's negative. And so the fix is to just simply take the numerator and factor out this negative 1. Okay, just like that. We do it, we write it just as if we were, and we are, we're using the greatest common factor. So minus 1, if we take that out of a minus x, it now becomes a plus x inside the parentheses. And a plus 3 divided by a negative 1 now gives us a minus 3. So now we have a factor that matches exactly, and we knock them out, the x minus 3's, and then we're left with a negative 1 and an x plus 3 on the bottom. Now you may be wondering, well, what about this x plus 3? Couldn't it have canceled out this minus x plus 3? And the answer is no. Yeah, they both have a positive 3, but again, this x is positive and that x is negative, the way it's written here. And so the x plus 3 won't even cancel this out. We have to factor out this negative 1 first. Okay. So, example 12, the top would factor as an x plus 5 and an x minus 5. and now we see the bottom is 5 minus x. It's backwards from this factor here of x minus 5 on the top. So what we're going to do, we keep the top the same, the bottom is the problem. We take the denominator and we factor out a negative 1. Okay, so negative 1, if I take that out of the x, x becomes positive, and then negative 1 divided into a positive 5 becomes a minus 5. Taking out this negative 1 just simply switches the signs. Okay, and I've changed the order of the terms here. If you didn't do that, then it would simply just look like this. 5 sorry, we'd have a minus 5 plus x. But you just have to realize that minus 5 plus x is just simply this x minus 5 written backwards. So this is the equivalent of x plus 5, x minus 5, negative 1, and reverse these terms and we have our x minus 5. So still those two cancel out, and we could write this as a x plus 5 over a negative 1, which really doesn't look all that good. We would rather just simply take this negative 1 and attach it to the numerator and not even write a fraction bar or a denominator. Alright, our last example. And sign wise, you've seen enough of these trinomials to notice that we're not used to seeing the x squared term have a negative. So just simply factor out the negative. It's going to simply just change the sign of each of the terms on top. Don't throw the negative 1 away. But now in this second step, we're going to factor. The bottom trinomial, it factors as a minus 4 and an x plus 1. And the top factors as a plus 2 and an x plus 1. 2 times 1 is 2. 2 plus 1 is 3. Likewise on the bottom, negative 4 times 1 is negative 4. And negative 4 plus 1 is negative 3. Okay. Taking out that negative 1 just makes this a lot easier to factor. So, but you don't throw it away. There's the negative 1 still. But in this step, we see that the x plus 1 is going to cancel. And we're left with a minus x plus 2 on the top and an x minus 4 on the bottom. And that completes example 13, and that was the last example of the chapter. Thanks for watching.